Hi everybody, I'm Giorgio Villani and the title of my research activity is Managing Networks of Peers for Data and Service Sharing. During these 3 years, I'm focused on two aspects. The first one is semantic query routing in a PDMS, and the second one is approximate searching over graph-based data. And all my research activities are carried out with members of IS group of the University of Modena. First topic, semantic query routing in a PDMS. A peer data management system is a peer-to-peer system where each peer is enriched by a schema dealing with the concept of the data stored in that peer. For instance, peer 1 in our reference scenario is dealing with data about music. Among peers, there are semantic mappings between concepts. In the graph, you can see that singer is mapped with vocalist term in peer 2, rock singer peer 4, and so on. So we can establish between all the concepts in one schema a mapping in the schema of the other peers. The query can come from all the peers in the network, and so we can collect them through semantic mappings. I focus on two main routing strategy targets, efficiency one and effectiveness one. The first one is trying to minimize the query paths, so we can try to reach all the best answers in the shortest path in the network. The other one, on the other hand, try to collect the best answer in the network without considering the path the query should go among the peers. To reach this information, we exploited a data structure we call SRI, Semantic Routing Index, which are matrices stored in each peer, and for each concept of the schema of the peer, provide a score of the goodness of the subnetwork routed by the neighbors of that peer. For instance, for the peer 1 and the concept singer of its schema, we can see that there we have 3 lines, peer 2, peer 3, peer 5, which are the neighbors of peer 1, and a score which expresses the goodness of the subnetwork routed by these neighbors. In this way, we can forward the query to the network in a semantic way. Here are the two main models we develop according to the two targets, and these are the DF model, the first model, which provide efficiency strategies to collect data among the network, and G model, global model, which on the other hand try to collect data in a more effective way. And so we can see from the example that, for instance, a DF model will forward a query about the concept singer. Now I'm speaking about just one concept for simplicity. And singer to the I-ranked neighbor, which is peer 2, which has a score of 0.8. And then in the first manner will propagate to the peer 4, which has a concept which approximates singer, rock singer. Notice that during the propagation we aggregate the results, and so rock singer will provide a goodness to the query about 0.4. On the other hand, an effective model will propagate the query to peer 3, not to peer 4, because vocalist is a better approximation to singer than rock singer, which is more specific. And so, but you see that we have one hop to the peer 1 back, and so to reach two terms we have spent 3 hops. Why to reach rock singer we spend just 2 hops? And this is in a very simple explanation the concept of efficiency and effectiveness. Here is a graph where I show that the policy we implemented can be tuned to a more efficiency or more effectiveness results. This is our system we implemented to test our proposal, which is called Sunrise, and you can see in the picture that we can create a PDMS, and we can query to a peer in the network a concept, and then propagate the query to the subnetwork, and see on the left part of the image the scoring we have reached during our propagation, and the number of hops we have done, and so on. We can select our strategies and in a very simple way. The second topic I deal with during my PhD is approximate searching over graph-based data. Graph-based data are, during last years, are very popular. For instance, biological databases, personal information management system, data spaces, and so on. This scenario of graph data have common features, which are largeness, like Antonio spoke before, and consider also the heterogeneity of the data. So we don't have one global schema which store all the data, but we have several different schemas. And so often a user doesn't have the knowledge of the vocabulary used, and also, as I said before, he doesn't know the structural and relational between data. So our goals are these two. We want to provide a very flexible way to pose query to the users, like in a keyword search manner, like Google. But we don't want to limit our search in a keyword search process or algorithm, but we want to allow user to include in his query also all the structural aspect he knows about the data. So if we want to see author and Alevi, these are two keywords, but we want to say that we want the paper authored by Alevi, and this is a more structural query. So what are the challenges of our approach? We want to provide an effective query model. So we want to provide the user with very effective, relevant answers, but also in a very efficient way. So this is about algorithm and the structure we exploit. And so we have to find this trade-off between these two aspects. We concentrated our experiments on RDF data, where we can see the main characteristics of graph data datasets. So we can connect graphs, parallel edges, node and edge with labels. These graphs are composed by entities, values, and relationship. Let me show an example to show what I mean. So we have this is a small portion of the DBLP datasets. We have documents, articles, journals. These are entities. And also we have values. For instance, these are instances of article, Alevi 04B, and which is connected through arcs by values. Alevi is the author of that instance of article, 2004 is the years of publication, and so on. The query model aims to go beyond, as I said before, keyword search, and we want to allow user to pose a query on the graphs, also allowing him to pose imprecise specification. So if I want, for instance, I want something related with this element. Let me show an example. These are two query examples. In the first one, I show an example of query with approximation of labels. For instance, I want a paper which is published before 2005, and the author sounds like Srivastava, which is a misspelling of Srivastava. So this is an example of approximation and relational operation on values, on labels. In the second example, I show an example of approximation on labels. For instance, I want two documents which are connected in some way, and this is the ball, yellow balls are on the example, and related in some way to the Piazza paper. So we have a paper titled Piazza and so on. Our model relies on approximate subgraph matching, as I said before. The approximation, as I show an example, are on the labels and on the structure. The labels, for the labels, we exploit a distance function. And for structural approximation, we exploit a structure which is semantic relateness, SR, which allow us to consider just the nodes which are meaningful related to each other. These are the answer of to the query I showed before. So we see that we reach Srivastava, which is a correct label. 1992 is correct for the range for the query, because we ask for paper which are published before 2005, if I remember correct. And we have also in proceedings. And also in proceedings is an approximation of the label paper. To exploit this label, we are based on the WordNet vocabulary. In the second example, I showed that we approximate also the labels of the query. For instance, we say that the two documents, which are one article and one in proceedings, so we have an arc of the query expanded into arcs in the data. And we say that this paper cite this other. Alevi 04B cite Srivastava 92C. In our scoring function, we consider approximation on data nodes, edges, and the query condition. This is a structure we exploit to reach the data in an effective way. We have an SR storing, which we pre-compute before in a not online way. And we have several indexes on these structures. The algorithm we exploit to provide queries are based on the threshold algorithm by Fagin, but we have several enhancements in our scenario. First of all, we have an object in one list can match to more objects in other lists. The second aspect is that one object which has matched in with another object can be deleted from the list, but can be matched with other objects in other lists to provide different answers. Finally, we implemented different strategies to build queries. We don't limit our model to the round-robin visit of the cursors, but we implemented next best policies. We try to minimize the approximation of the labels, and another policy which we call max selectivity, which considers the cardinality of the cursors. Yeah. In the table, you can see some data about the effectiveness of our approach in comparison with the exact query model. Exact in the first part, we have a data set about Russian novelist, and in the bottom we see some data from the DBLP dataset. We see that with respect to one query of our model, we have several queries in an exact way, an exact query search engine. Further, for the web, in comparison with respect to the DBLP dataset, we see that a query of our model corresponds to several requests to the user. For instance, we asked before for an author, and then for the year, or for the co-author, and so on. Here we see that our model can reach always a very high precision, a very high recall in comparison with the other model. Here in the graph I show the effective the efficiency of our model. We compare a sequential access to our cursors on SR to the indexed access to our cursors. We see that our three policies are really better than the base mode. In the graph, we can see that the policy which considers the cardinality of the cursor is the best one. Also, consider the number of access to the indexes are confirm our what I showed you before, speaking about times. And so also in this slide we see that the number of access to the indexes is very small in case of in our policies, and the max cell policy is always the best one. Just to conclude, I show you in the second part of this presentation the effectiveness of the efficiencies of our approach on an RDF-based data set. And I try to compare our approach with other keyword search, exact keyword search, and other in web portals. I didn't show examples on literature, other literature graph-based model. Our approach is more flexible and expressive in query formulation than the other model we consider, and avoid user interaction. User can only ask for one query, and our system will provide all the queries which are relevant for him. These are my publications. And so, yeah, thank you.
Thank you, Giorgio. Questions?
Which is the degree of dynamism in your approach? So can the peers join and leave the network dynamically, or they must be present?
There is a paradigm in Sunrise which manage all the insert of a peer and the deletion. And so when a peer insert in the network, all the changes in the structure of the schema will propagate to the neighbors.